In section 11.1, we discuss what happens when a solute dissolves in a solvent. That is, we're going to be discussing the dissolution process. You've probably noticed that for living organisms, it's important to maintain the concentration of solutes within narrow limits. For example, if your electrolytes get depleted, you get muscle cramps and you start feeling pretty lousy fairly quickly. Similarly, if you have trouble maintaining your blood sugar level, that is, you are diabetic, then again, if your blood sugar level gets sort of outside some pretty narrow limits, you start feeling unwell. But the question that is worth considering at this point is, why is it that we restore our electrolyte levels by drinking an aqueous solution containing electrolytes, but when we need to adjust our blood sugar and we need to take some insulin, we're going to inject that insulin into a fatty part of our body like our belly or our thighs or our upper arms or perhaps our buttocks. So why is it that electrolytes, ionic compounds, have good solubility in water, but insulin, a small peptide, we're going to inject that into a fatty part of our body? What is it that makes these solutes soluble in each of these solvents? So we should think about the energetics involved in forming a solution. The formation of a solution can be thought of as occurring in 3 steps. First of all, we're going to make space in the solvent for the incoming solute particles. That is, we're going to move the solvent molecules away from one another by breaking some solvent-solvent interactions. And whenever we break any kind of bond, we have to put energy in, and so that will be an endothermic process. Now what we need to do is we need to separate the solute particles from each other. So we need to disperse our solute particles, and doing this will break some solute-solute intermolecular forces. And again, that's going to be an endothermic process and require energy. And then finally, in step 3, we disperse the solute throughout the solvent, and we put the solute particles into the spaces that we made in the solvent. And this is going to result in the formation of solute-solvent interactions. So new intermolecular forces will form, and the formation of bonds is always exothermic. So we have 2 processes that require energy and one that produces energy. And the key thing is, as long as we get more energy out at step 3 than we consume in steps 1 and 2, then the substance will be soluble. So if the strength of the solute-solvent interactions is strong enough to provide the energy for disrupting the solute-solute interactions and the solvent-solvent interactions, then the solution will occur. So let's think about what happens when we dissolve methanol in water. So methanol has this Lewis structure. And we can see that due to the presence of the hydrogen bound to the oxygen, that methanol can hydrogen bond. Now, water, of course, can also hydrogen bond. So what that means is the types of forces, hydrogen bonding, that we're disrupting amongst methanol molecules and amongst water molecules are similar to the type of forces that we're creating between water and methanol molecules when we mix these guys together. So that means that the type of solute-solvent interactions that we're forming is similar in energy to the types of interactions that we're disrupting, and so as a result, the solution will form. So the general rule of thumb is that polar solutes will tend to dissolve in polar solvents as they can form strong dipole-dipole interactions with the solvent. and that non-polar solutes tend to not dissolve in polar solvents because they are unable to form strong interactions with the solvent. So a good example of this is if we take water which is polar and combine it with something like octane, which contains only carbon to hydrogen and carbon to carbon bonds, which is non-polar, what you'll find is that the octane won't dissolve in the water. It'll just float as a layer on top, and then the water will sit underneath that, and the two just won't mix. Now, we sort of talked about this before when we were talking about ionic compounds. We said the reason that an ionic compound dissolves is the result of formation of strong ion dipole interactions between water molecules and ions that are at the surface of the crystal. So we put all of this together, and this is often summarized by what we call like dissolves like, which basically states that polar solutes tend to be soluble in polar solvents, whereas non-polar solutes tend to be soluble in non-polar solvents. Previously, we talked about the role of dispersion forces in aiding the solubility of oxygen in water. It's important to realize that dispersion forces are quite weak and are easily disrupted. What that means is that if you raise the temperature of an aqueous solution of oxygen, the concentration of oxygen will decrease because these bonds will be disrupted by the movement of the particles that is increased as the temperature increases. And this is actually kind of a general rule that the solubility of gases decreases with temperature. And you've probably noticed this, that if you have a bottle of soda and it gets warm, it loses its bubbles. And that's because the CO2 is lost from the solution. You may also have noticed that if you warm some water well below the boiling point, you'll see bubbles of gas leaving the water. And so this is summarized in this diagram here, where we can see that the oxygen solubility is radically increased as we increase the temperature of water. So if we start at sort of like, let's say, around about 20 degrees Celsius, and we've got a solubility there of about 9 milligrams per liter, and we raise the temperature to, say, 40 degrees Celsius, well, we've dropped down by about a third. So we've reduced the oxygen solubility down to about 6. So you can see that the effect is quite dramatic. So as the temperature rises, the oxygen molecules and the water molecules gain sufficient kinetic energy to overcome the dispersion forces holding them into solution, and the oxygen leaves. And if this happens on a big enough scale, you can get these really awful fish kills. So collectively, interparticle forces or intermolecular forces are often called van der Waals forces. Furthermore, these intermolecular forces are often divided into forces that reduce solubility in water. These were going to be between nonpolar molecules. And these are described as hydrophobic forces, hydrophobic meaning water-faring, or the forces between polar molecules that increase the solubility in water, which are described as hydrophilic interactions, which means water-loving. So every type of intermolecular force is kind of collectively referred to as being a van der Waals force. Those that decrease solubility in water, the non-polar forces, are called hydrophobic forces, and those that increase solubility in water, i.e. the polar forces, so hydrogen bonding dipole-dipole interactions, they're referred to as hydrophilic interactions. So it's the overall balance of hydrophobic-hydrophilic interactions that will ultimately determine the solubility of a solute in water. So if we look at a structure like ethanol, the structure is dominated by this OH group, which gives it hydrogen bonding capability, and hydrogen bonds can form strongly between ethanol molecules and water molecules, and as a result, ethanol is completely miscible in water. If we look at something like octanol, here's the Lewis structure of octanol at the top here, we still have these OH groups that can hydrogen bond to water, but the structure is dominated by this non-polar carbon-hydrogen chain, which creates a lot of dispersion forces, which are hydrophobic. And as a result, octanol is not very soluble in water at all. So that concludes the video for section 11.1, which is concerned with the dissolution process.